Welcome. In this video, we're going to start the study of the definite integrals. Now, before you go ahead with definite integrals, it's important to note that when we're talking about definite integrals, we're talking about integrals that are bounded. And thus far, we've only covered derivatives that are unbounded. So, what that means is that we have discussed in the first video of this series that using the integrals, we can find area of a given region, and sometimes we can even find the volumes of certain solids using triple integrals, which we're going to cover in the later videos. So if we have any function, let us say you have a function y is equal to x, well, we should not assume that this function starts from here and it ends here. Actually, this is an infinite line that stands from the minus infinity and goes to the plus infinity. So if you want to use the application of the integrals as a way to find areas, this becomes very difficult for us to find the area of a region that is not bounded. You're finding an area of a place in which you have to measure, and you never find an end. So it's hard to give a definite value to that situation. But on the other hand, we have what we call as definite integrals. Now, in definite integrals, we have an area in which we want to find, the area which we want to find is bounded. So we have a starting point and have a finishing point. So because we have a starting point and a finishing point, now we have a definite value, a fixed value of that given area, and because we have a fixed value of that given area, we don't have the constant c of integration. So from these functions here, if you find all these functions have the same derivative. Now, if using this derivative we were trying to guess what was the original function, what we do is just we use the integrals. Now, if you find the integral of this, it should give you back this same function. Now, finding the integral of 2x. Find the integral of 2x dx, because we're dealing with respect to x. So this is going to be equal to, this x is a constant, it comes down, and then we're going to use here the property which is the power rule for the integration. So it's going to be x raised to 2, because we're increasing power by 2 here, and dividing this also by 2, and then you cut this, and then this you're going to, let's leave for now. So you simplify this. So as you can see, if you take this derivative of these functions here as our starting point and find the integral to try to go back to the original function, we can see that though all of them have the same derivative, they give us different functions. So this is different from this, is different from this, but if you take this as the starting point, these derivatives, we are getting that we're having the same function, which is not true. So in this case, it means that we have some constant, but we don't know. In this case, because we know the function, this constant would be 0. In this case here, the function, the constant that is here is 1, but we didn't know that. And same thing can happen here, and we have a constant 3. So it can be any constant here. We are not sure what is the constant there, but we know that there should be a constant. Fine, so that's why we have this. And this can be applied for certain functions, like this function, for example, can say f of x. It's unbounded, so we are finding an area from a certain region to the infinity, which is not possible. Now, in definite integrals, we are dealing with a restricted area. So we're dealing with a point from here, this should be straight, from here to here, for example. So if we are finding the area, we are finding the area of this region alone, only this region. We can see this is our point A and this is our point B. And because we are dealing with a limited area or a bounded area, this symbol that we use, the symbol of integration, it changes. Now it becomes the integration from A to B of a given function f of x, and then you're going to get the result, and this result that you're going to get here is the area of that region, and this is the x, because we're dealing with x. This is going to give us the area of this region that is bounded, not the whole area covered by this. And as you can see, because this area here is bounded, therefore we can have a value. We don't have something unknown, we have constant value. But if this area was not restricted, we are just evaluating without having a beginning and end, and therefore it's difficult, or it's relative, to have the value of that given function. What this implies to a function is that, imagine that you're solving an integral. We can take an example like this one. Let us say you have integral of 8x squared dx, because we're dealing with respect to x from a point 2 to a point 5, 2 to 5. So these are our limits. This is the lower limit and this is the upper limit. So what we do, same rules I've used in the beginning for indefinite integrals. 8 is a constant, so we take it out. We have 8 and then we continue having our sign of integration to 5 of x raised to 2 dx. This is equal to 8. This is the difference now. With this x squared, this is the power rule, so we're going to have x3 divided by 3. And the limits or the boundaries we have are from 2 to 5. Then that's how we solve it. So it's different from the other case, so we don't have a c here. And this is going to be equal to 8 into, now how do we evaluate this function using the limits? Now you take this, whatever the value we have obtained here from the integral, you want to replace wherever you have x or whatever the variable you're dealing with the upper limit minus the same thing with the lower limit. So what you're going to get here is 5 raised to 3 divided by 3. This is one part of it divided by 3 minus the second part of it is 2 raised to 3 divided by 3, and this is what you want to get. Now with this you're going to get 8, so you have here 5 raised to 3, so this is equal to 5 raised to 2, which is 25 into 5, so this is going to give us 125 for this first member here divided by 3 minus we have here 2 raised to 3, which is equal to 2 raised to 2 into 2, so this is going to give us 8 divided by 3. This is a common denominator, so we have 125. We have 125 minus 8 divided by 3, and this is equal to 312. This is a fixed value we have, which is the value of the area of the region bounded or bounded by a curve defined by this function. And in this given case we don't put any c because we know exactly what is the region and what are its boundaries. In the upcoming video we are going to discuss some of the properties and the rules that we use when you're dealing with definite integrals.